all the way from the United States, Mr. Kirk Sorensen, the founder of FLIPE Energy Systems in Alabama. Kirk is in fact, was a NASA space engineer. And during his quest to find a power source, he stuck upon the thorium reactor. And he was one of the first to recognize the potential.
Let me just review a few of the amazing discoveries that have brought us here this day and give you a sense of when they happened and how far back this goes. It begins with Glenn Seaborg at the University of California in Berkeley, who first discovered uranium-233 from, that it could be formed from thorium. And he also discovered that it was fissile and that it was possible to form a breeding cycle from this. And these amazing discoveries were happening, though, in a period of war. And so the question was, could it be applied to wartime purposes? He also discovered the issue with uranium-232 contamination, and this is what caused thorium and uranium-233 to be set aside for the remainder of the war as something not applicable for nuclear weapons. Nevertheless, it was very applicable for nuclear power reactors. And this was picked up after the war at Oak Ridge National Laboratory under the direction of Alvin Weinberg, who originally, his chemists conceived of the molten salt reactor and realized that they would have some tremendous advantages. They built the first molten salt reactor in 1954, and not long thereafter, they began to realize that thorium and the molten salt reactor ideas could be brought together in a new concept, the thorium molten salt reactor, and that this would make an ideal reactor for generating electrical power for civilian use, for people. And so they started a program in 1957. They discovered a material, they called it INOR-8, we now know it as Hastelloy N, that it would be suitable for molten salt reactors, and it would be able to carry the materials in a sufficient duration. They built a reactor out of Hastelloy N called the Molten Salt Reactor Experiment in the early 60s. They ran it until 1969 when they were ordered to shut it down, even though it was still running very well. And they continued their studies into the 70s when the whole program, unfortunately, was canceled because of a change of priorities in America as far as funding. And this had a ripple effect on other molten salt reactor programs that were taking place around the world. As we now know, even in China, they were working on molten salt reactors, and they set their work aside after the Americans stopped working in the early 70s. So I was born in 1974, which unfortunately was the same year the molten salt reactor was shut down. The whole program ended. So I can kind of mark the beginning of my life as the beginning of the end for the molten salt reactor. So I'm 40 years old, and it's been 40 years. We're 40 years past due in getting this job done. And that's another reason I feel such a passion to work on this, is because we're far behind schedule, and we want to power the world with thorium, and we want to eliminate so many of the political and social problems that have come about because of our dependence on other energy sources. Political mistakes and poor information led to the cancellation of molten salt reactors. It was not a technological problem. And many of the key materials compatibility questions were answered to satisfaction during the operation of the molten salt reactor. Safety, as we know now, is something that is paramount in the minds of the public. This is something that perhaps was not getting enough attention in the early 1970s. Now we know that if we want to have the public accept nuclear reactor technology, it has got to be very safe, and it has got to be something that is easily explained to people. Now, I've explained the safety basis of the molten salt reactor to people many times, and I haven't had anyone who's been unable to get it, except for some PhDs who sometimes struggle with the idea. But all regular people seem to have no problem understanding the drain and the salt and so forth like that. I'm convinced that the molten salt reactor represents the best confluence of performance, safety, and technological readiness of any of the reactors on the drawing board right now. And obviously, I know I must share this enthusiasm with many of you in the room, otherwise we would not be here. But I hope that we can go forward and share a lot of this enthusiasm and message with other people. To introduce thorium, thorium is about 3 times more common than uranium, and if you consider the very tiny sliver of uranium that we're using now to power reactors, this little tiny bit of uranium-235, then it's vastly more common than that. But only all of this thorium, though, is fertile, along with the majority of the uranium, and these can both be converted into fuels for nuclear energy. This is the discovery that Glenn Seaborg made in the early 1940s, that both thorium and uranium-238 could be converted into fissile materials and have an energy release. The downside, though, the difference between the two, was that only thorium could produce enough neutrons in the fission of its daughter, uranium-233, to sustain this process. Plutonium simply did not produce enough neutrons. In order for plutonium to produce enough neutrons, you had to go to what's called a fast reactor. And this has led to, traditionally, the interest in fast spectrum nuclear reactors. They are the machines that allow uranium to potentially be sustainably consumed because they increase the number of neutrons available from the fission reaction. There's a big disadvantage, on the other hand, though, to going to fast reactors. And that is that nuclear fuel itself is far less reactive to a fast neutron than to a thermal neutron. So, I'm a simple mind. I wanted to draw a simple picture. This is what plutonium looks like to a thermal slowed down neutron. And this is how many atoms of plutonium it would take to equal that same probability of absorption in the fast spectrum. Every single plutonium atom looks tiny to a fast neutron, but they look very big to a thermal neutron. So there's a big advantage there to going ahead and saying, let's look at using a thermal reactor, and thorium being the only fuel that can be sustainably consumed in a thermal spectrum reactor. And this was covered earlier by some of the wonderful speakers this morning. Now, sustainable consumption of nuclear fuel is essential if we are going to reduce the production of long-lived nuclear waste. Actinides, as was earlier mentioned, constitute the bulk of the long-lived nuclear waste risk. If we can exclude actinides from the waste stream, then the decay of fission products reaches a level of natural ore in only about 300 years. So how do we sustain a breeding cycle, a fuel consumption cycle, and how do we keep actinides out of the waste stream? These are going to be some of the subjects of my presentation today. 3 paths. The path we take now, which is burning this very, very rare amount of uranium-235, or the path that has been investigated by a lot of advanced nuclear programs, the idea of burning in a fast reactor uranium-238, or this new idea, well, this new old idea, I should say, which is using thorium in a thermal spectrum reactor. So let's look at each of these 3 fuel options through the perspective of a molten salt reactor, assuming we are going to use a molten salt reactor for each case. We could imagine fueling a molten salt reactor with low enriched uranium. If we do that, the uranium mining and enrichment necessary will be comparable to what we do today in light water reactors. So there's really not going to be a big delta or difference between what we're doing now as far as from a mining and enrichment perspective using today's reactors or using molten salt reactors if this is our fuel form. There's another challenge too, and that's also how are we going to add uranium-235 fuel, because that's really what's running the reactor, and discard uranium-238 while retaining plutonium and these other transuranics. How are we going to keep the actinides in the system? Because you've got to move a lot of material through a reactor like this. Option 2, we could imagine fast spectrum molten salt reactors. These have been considered. In these cases, we would not need any more uranium mining or enrichment, but we're going to have a high inventory, because as I mentioned earlier, each of those fast neutrons, fuel looks small to a fast neutron. And there are chemical separation issues with fast spectrum molten salt reactors that are going to be challenging. It's harder to get plutonium and uranium away from one another in fluoride than it is to get thorium and uranium away from one another. Chloride still is another option. And finally, option 3, which is obviously the option I favor, which is the thorium-fueled thermal spectrum molten salt reactor. No uranium or mining or enrichment are going to be necessary once we're in steady state, and this option will have the lowest of all of the fissile inventories. And that fissile inventory won't be plutonium, it will be uranium-233. The chemical separation is straightforward. In each case, what is our waste profile going to look like? It's going to be strongly dependent on the chemical processing strategy. But the chemical processing strategy I'm going to outline today is based around thorium and the thorium fuel cycle. So as I mentioned before, low enriched uranium is going to require much more uranium mining, much more uranium enrichment. If we go fast spectrum, we're not going to need the uranium mining or the enrichment. We're going to need efficient chemical processing, but we're going to have the largest fissile inventory of plutonium, and that's what it will be. This is a picture of the Rocky Flat storage facility where the U.S. used to keep a great deal of its plutonium. But with the thorium molten salt reactor option, no mining, no enrichment, no thorium mining either, because thorium is recovered from rare earth mining operations. And rare earth mines are already bringing up so much thorium, it's vastly in excess of what we're going to need to power the entire world on thorium. So even thorium mining is not going to factor into this. We are going to need efficient chemical processing and fissile recovery to make sure that we can turn some of today's fissile resources into fuel for future lifters. And this option is going to have the minimum fissile inventory of any of these options, and that fissile material will be uranium-233. So I would make the case that we need to choose very wisely if we want to entertain having a future nuclear-powered society, what our fissile currency will be. Is it going to be uranium-235, which is rare, which we obtained from natural uranium via enrichment? That first path was weaponized, and it continues to be a concern, as we see today with the discussions going on over Iran, how sensitive the idea of uranium enrichment is. The second path, are we going to breed plutonium from natural uranium in a fast breeder? A variation of that path was also weaponized in the production reactors at Hanford. and in other countries as well, and it continues to pose international concern as we see in North Korea. Or will we choose uranium-233 as our fissile currency from thorium in a thermal breeder reactor? That third path was not weaponized because of the unavoidable contamination of uranium-232, which was realized by Glenn Seaborg in 1944. And it would not be weaponized by a nation-state because there are much simpler alternatives, in other words, enriching natural uranium or making plutonium. And it would not be weaponized by a subnational group because they would have no idea if their design would detonate, and testing would be necessary, which would be far beyond their resources. So I would make the case that if you have to choose your fissile currency from one of these three options, the safest and best bet and most efficient is to use uranium-233 and to choose the thorium option. If we are going to make this decision, which poses the biggest threat in the long term? Will it be plutonium or will it be uranium-233? I would say uranium-233 represents the safest option. It was never used in production nuclear weapons, and only in a handful of experiments whose results were of dubious performance. And this is another one of the reasons why it was not considered. Let me introduce the work I'm doing on the liquid fluoride thorium reactor. This is based strongly on the work that came out of Oak Ridge National Labs in the late 1960s and early 1970s. They had investigated two different kinds of thorium breeder reactors. They called them generally the two-fluid and the one-fluid reactors. In the two-fluid reactors, there was a separate blanket that contained the thorium and a fuel salt that contained the uranium-233. They abandoned the two-fluid design thinking it was too challenging and went with the one-fluid design later. And the one-fluid design seemed to offer a simpler core design, but the chemical processing was more complex. I have become convinced from my research since 2004 that the two-fluid design, despite its core design challenges, represents the best bet in the long run. And I'm going to try to talk a little bit about that today. Here is the impetus that is moving us so strongly, though, towards thinking about what are we going to do with our nuclear future in the United States. We call it the retirement cliff. The United States has more nuclear reactors than any other country. It used to be over 100 reactors, but it's just in the last few years, retirements have increased. And this graph is several years old, and the accelerating pace of reactor retirements is going to mean that the United States is going to lose its nuclear capability within the next 20 to 30 years. If you value nuclear energy as a carbon-free energy source, as a reliable energy source, as a cost-effective energy source, then this effect has to be mitigated. There has to be the construction of new nuclear technologies in order to compensate for the retirement cliff. But what should those be? It's commonly believed, this is a copy of The Economist I got a couple of years ago that said nuclear energy, the dream that failed. Ladies and gentlemen, this is incorrect, all right? This is absolutely not right. And I want to cement that in your minds, that nuclear energy is not the dream that failed. If anything, it is humanity's best hope for the future. And as an aside, I have to wonder why when I see an oil spill or a natural gas explosion, I don't see on the cover of The Economist next week, natural gas, the dream that failed. But that's an aside. Nuclear energy is a big space, and there's a lot of different ways to design nuclear reactors. We happen to have chosen really one, maybe two of these routes, but there is a big design space there, both in solid and fluid fuels. And when we talk to people about nuclear, we have to help them understand we're thinking about that big family of options, not just about the one or two that they may know. In my company, we believe in the vision of a sustainable, prosperous future powered by these advanced nuclear reactors, and we think thorium is the best way to go. There will be products from these reactors beyond electricity, particularly things like desalinated water, perhaps even chemicals, hydrogen production, medical radioisotopes, and a variety of other useful items that can come about from the production of these reactors. I formed Flibe Energy in 2011 in order to develop this technology because I was not seeing it going forward in the United States, and I wanted to change that. Our goal is to provide the world with affordable and sustainable energy, water, and fuel. This is the machine that we would like to design. This is the liquid fluoride thorium reactor. It has a reactor vessel made of Hastelloyen, which we talked about earlier today. Because of the issues that were brought up about Hastelloyen, we know that we have to protect this material from the difficult environment it's going to encounter inside the reactor. And so that's why the overwhelming majority of the interior of the reactor is composed of graphite structures. Graphite structures that separate the fuel that flows through these recursive tubes from the blanket. And the blanket fluid surrounds the entire core of the reactor. It's hard to see the boundary between the blanket and the core, but that blanket protects the metallic structures from the radiation damage that was discussed this morning. It protects the metallic structures from neutron flux. It basically keeps that nuclear reaction bottled up in a region of the reactor where it's not going to cause nearly the damage to materials that it would otherwise cause. For instance, in a one-fluid reactor where you could have fission occurring right up to the very edge of the metallic structure. In a two-fluid reactor, there's a lot of thorium-containing fluid between the edge of the core and the reactor wall that absorbs neutrons, gammas, and radiation flux and prevent it from damaging the material, because we know that metal does have some severe issues when it's close to the nuclear reaction. Nevertheless, there's going to be other metallic structures. There's going to be primary heat exchangers and so forth. But once this fuel leaves the reactor structure, fission stops. And so there's not an appreciable neutron or radiation flux outside the reactor to nearly the degree that there is inside the reactor. So graphite is a very important structural material in this design. It has two different fluids. The primary fuel salt is a highly depleted lithium fluoride, beryllium fluoride, and uranium tetrafluoride. And that uranium is mentioned by Dr. Kloosterman is a combination of uranium-233 and a number of other uranium isotopes. The blanket fluid is highly depleted lithium, beryllium, and thorium tetrafluorides. And that's where that nuclear absorption of neutrons is taking place in the formation of new fuel. The coolant salt is highly depleted lithium beryllium, simply call it bare flab. And that coolant salt then is very chemically compatible in the event that there's ever an in-leakage into the fuel or into the blanket, because it's essentially the same solvent of which the blanket and the fuel are composed. The design objectives for this reactor is about a 250 megawatt electric or 600 megawatt thermal core, a conversion ratio of 1 or greater, pretty close to 1. We don't want to, we're not designing this to be an appreciable breeder. We're designing it to make as much fuel as it consumes. The design life is yet to be determined because of issues about the material concerns. Fuel salt is separated from blanket by graphite tubes. And very importantly, the graphite and the thorium blanket shield the reactor vessel from the thermal neutron flux. And that's an important consideration when thinking about the limitations of metallic structures in molten salt and in a nuclear environment. This is an overall view of the modular nature of the lifter facility. There's the reactor vessel, drain tank, pump, primary heat exchanger. This is the gas heater. It heats carbon dioxide. There's the carbon dioxide gas turbine. These are chemical processing facilities for the fuel salt and the blanket salt. And then these are off-gas processing facilities for the xenon and krypton that are going to come out of the fuel salt during operation. The entire reactor cell is located below ground in a shielded structure and shielded against external impacts and events. The chemical processing system, this is notional, but it shows some of the steps that will take place in the chemical processing system. These steps include the reductive extraction of metals from using metallic bismuth, and then the fluorination of the fuel salt using fluorine gas to remove uranium and other gaseous hexafluoride components. There's also electrolytic cells that will be used to restore reductants back to the metallic bismuth, and electrolytic cells that will be used to break apart hydrogen fluoride back into reactant gases like F2 and H2. This is the overall processing and flow diagram of the lifter. As you can see, the two regions here, there's the fuel salt region, and surrounding it in kind of the turquoise blue is the blanket salt region. In the blanket salt, protactinium is formed from neutron absorption on thorium in the blanket. That blanket salt proceeds to a reductive extraction column where it's contacted with metallic bismuth that will remove protactinium and any uranium that's present there and return a cleaned up blanket salt back to the reactor vessel. That metallic bismuth stream then proceeds through a series of additional reductive extraction cells and electrolytic cells before ending up in a decay tank. In the decay tank, we give the protactinium time to decay to uranium-233. And actually, there's several other protactinium isotopes in there as well, 231 and 232. 232 will also decay to uranium-232. So uranium-232 is still present even in the decay tank of the blanket because of its or even the decay tank here because of its formation in the blanket. As uranium begins to grow in the decay salt, though, it is removed through fluorination, and then it's added to a stream. And let me pick up from the fuel salt's perspective. Fuel salt is taken out, and it is fluorinated also to remove uranium and other gaseous hexafluoride products. Those two streams are joined at that point. The remaining fuel salt, now stripped of its uranium, goes to another reductive extraction column where metallic bismuth is used to remove lanthanides and long-lived fission products. And then that stream is returned to a reductive extraction unit where the UF6, the fuel salt, and hydrogen gas is used to reduce UF6 back to UF4, bringing it back into solution and essentially refueling the fuel salt and sending it back to the reactor vessel. The HF that is produced by this reaction goes to an electrolytic cell where it is split back into H2, which is used again for the reduction, and F2, which is used for the fluorination steps. So all of this forms a closed cycle. This explains how the chemical processing takes place. The power generation takes place when fuel salt is pumped through the primary heat exchanger. It then heats the coolant salt I mentioned earlier, which is just bare flib. That bare flib then proceeds outside of the containment and heats carbon dioxide, supercritical carbon dioxide gas, at about 550 degrees C turbine inlet temperature, which then proceeds through a supercritical carbon dioxide recompression turbine cycle. And that is a highly recuperated cycle that has 2 recuperation stages and 2 compression stages. But ultimately the gas is cooled, compressed, recuperated, and reheated in a closed cycle. The performance of the carbon dioxide gas turbine is such it leads to very, very compact turbo machinery. The turbo machinery for this entire reactor would easily fit on this stage, probably on half this stage. And if anybody's been to a big reactor before and seen big steam cycle turbo machinery, you can appreciate what a reduction in scale that is. It's about 45% efficient too, which is really, really attractive. So these 3 processing objectives, I mentioned the 3 reductive extraction columns, 2 fluorinators, the hydrogen reduction column, and the electrolytic cells. All of this is designed to close the thorium fuel cycle inside this machine. As Dr. Klusterman mentioned earlier, we're not going to be moving materials off the side outside of the containment vessel. We're going to be taking care of all of these chemical processing steps inside the reactor vessel, inside a closed environment. And really the only application needed is electricity. Electricity to split electrolytically some of the components that then chemically drive the operation of the entire cycle. Fission product off-gases were also mentioned in the last talk, and it's important for these to be removed along with the noble metals that they sometimes contain and also held for a period of time, about a month for xenon, and this is a notional design for the off-gas processing system for the lifter. If we are able to accomplish these goals and to implement the thorium fuel cycle at this level of efficiency, let me try to give you a vision of what this can mean for the future. Imagine a cubic meter of common continental crust found anywhere on Earth. So this is average Earth anywhere. Inside a cubic meter, on average, there is about 2 cubic centimeters of metallic thorium and about half a cubic centimeter of metallic uranium, if we were to reduce them to metals. Obviously, they're oxides in the Earth. But if these 2 cubic centimeters of thorium were used as fuel in the lifter, as so described, they would have the energy equivalent of over 30 cubic meters of the finest anthracite coal or crude oil out there. In other words, transforming average continental crust into an energy resource that surpasses the finest energy resources we know of from a chemical basis. This is an absolutely incredible opportunity then for the human race to now realize an energy source that is so vastly in excess of what we have from our finest chemical energy sources. And Alvin Weinberg called it burning the rocks. Glenn Seaborg realized this in 1944, and he was absolutely dumbfounded with the possibilities of what it meant for the future, what it meant for, here he was watching nations wage war against one another in World War II and realizing that this could be a complete game changer and change the entire energy outlook of the future. Now, of course, there are challenges that remain before us before we're going to be able to build these reactors. Obviously, we need to get the materials code qualified. We need to work on almost every system of the reactor because the work was set down, as I mentioned, in 1974, and only recently, at small scale, has it been picked back up again. Several key issues that I would really like to call attention. We need to be able to isotopically separate lithium, and that's in order to reduce the amount of tritium production. We need to preserve our existing uranium-233 inventory. As modest as it is, we need to be keeping it. And we need to have a greater investigation of fuel cycle safeguards for this system. I'm confident they can be implemented, but there needs to be a lot of work done on that. In the medium term, we need to be working on the power conversion system development and each of the steps in the chemical processing system. I would also like to see greater investigation of an integrated desalination cooling system with the gas turbine. That way we could use that 55% of thermal energy that's coming off the gas turbine and put it to productive use, generating clean, fresh water. In the longer run, we're going to need to build this materials database lifetime in order to build reactors that are going to last 10, 20, 30, 40 years, finding out which things are important and which things we can mitigate through proper reactor design and proper temperatures. I would like to see us investigating burning up plutonium in molten salt reactors for waste reduction and uranium-233 generation. And I ultimately dream of things like molten salt reactors powering cargo ships. So in conclusion, I'd like to leave you with some important thoughts. Only thorium MSR is going to allow us to produce nuclear power without plutonium. There are no other options to making nuclear power and not making plutonium other than this approach. In the 43 years since 1972, the potential of this technology has not diminished, but we are faced with the consequences of our inaction. I worked 10 years working on technology development at NASA. And one of the messages I wanted to convey to people was technology doesn't develop on its own. It develops when we push it. And the converse is true. When we don't push technology, it doesn't go anywhere. We're facing 40 years of inaction, and we need to restart technology development and work on solutions to these technology challenges. My personal confidence is very high that we will find acceptable solutions to these issues. We will be able to address them and ultimately implement the thorium MSR and realize its incredible advantages. Thank you very much, and I greatly appreciate your attention.
Mr. Sorensen, thank you so much for this extremely informative and energetic presentation. With a power such as yours, I'm sure we will have this MSR in, well, the very near future.
Yeah, my name is André Bosman. One of your beginning slides, you said this invention didn't go through because of poor political choices. I'm a member of parliament, so I'll be one of your decision makers. How do we transform the idea about nuclear energy, because that's what we call it, it's nuclear energy. And if I discuss nuclear energy within the lower house, everybody thinks about Fukushima and 3 Mile Island and all the problems associated with it. How do we educate people that this is a different type of nuclear energy with the potential for the future?
I don't envy you your challenge. I think your challenge might be much greater than mine. You have asked exactly the right question. How do we educate the people on this? And I wish I had a very succinct answer, but I will say I think there are a number of advantages that we have in 2015 that were not present in 1995 or 1975 or 1955. The first one of those being the Internet. We have a way to produce high-quality informational videos and get them out there. I was particularly impressed by a piece on radioactivity that was done, I think, by the Canadian Nuclear Safety Organization last year, and it just explained radiation in very simple terms. It was very accurate, but it did it in a way that diffused people's fear. It helped them understand radioactive materials are part of the real world. And I looked at that and I thought, wow, this is the kind of thing, we need many more of these things. We need them in Dutch, we need them in French, we need them in German, we need them in English, we need them in Portuguese and Japanese, and we need to be explaining to people, here is why nuclear energy is not a strange, bizarre, terrible item. Often when I give this presentation, I begin by showing how we are able to have life on Earth now because of the behavior of uranium and thorium inside the Earth's crust, keeping the Earth molten, and helping people understand these natural flows of energy that have kept our world habitable. We have to thank nuclear radioactive materials for this. So before you think, oh, this is awful, our planet would be as dead as Mars without radioactive materials that have been present for billions of years. So that's one of the things I like to do to help begin to explain to people that these are not strange and abnormal substances. These are part of the world that we live in, and they've been responsible for many good things that we enjoy. In fact, the existence of life on Earth can be directly traced back to that. To help them then begin to understand that nuclear is not strange or abnormal or unnatural helps begin to move them into the idea of how we can harness nuclear fission for energy, and why the fact that nuclear fission does not release carbon dioxide, that it is a controllable technique, and that it is something that if we use the fuels properly, as I explained here, the supply of fuel will literally last hundreds of thousands, if not millions of years. The technologies we've talked about today are controllable. In other words, they can be implemented into an energy grid with other energy sources, particularly energy sources that may not be as reliable. That's an advantage. And an economic argument to appeal to constituents as well, to say, wouldn't you like your country to be able to own its own future in terms of energy supply. Many countries, my own included, are highly dependent on other countries for their energy supply. And most every country I've spoken to would really like to be energy independent. This is a technology that allows any country to become energy independent. I would wager to say even within the borders of Luxembourg, there are enough thorium deposits in order for Luxembourg to be energy independent if they so desired, although thorium is very cheap and there's lots of places you can buy it outside of Luxembourg. But this is something that perhaps I'm kind of throwing ideas out here, but I hope some of these may be useful because, as I said, you have a very difficult job, and yours is most important because as a leader, you will have to convince the people to think seriously about this as a future possibility.
People from the media are as quickly writing as you are talking. That's what I noticed.
My name is Toussaint. My question is, hearing all this, why isn't capital not flowing into the development of these type of reactor?
Well, there are some flows of capital that are following this. If I might trace back to the last question, though, in most of the countries that I've traveled to, the first question that investors have had for me is, what will the government think of this as we go forward? And I want you to know, as a preface to that, I fully accept the role of government licensing and regulation in nuclear. There is simply no future we can imagine where governments do not license and regulate nuclear energy. So that is a given. What needs to happen, though, is there does need to be improvements in licensing regimes, and probably several of the other speakers today are going to talk about that make it more transparent for capital markets to be able to say, if we do this, what can we expect to happen? Or what, as a licensed regulator, do you want to see take place at what stages? And we will go and try to show that to you. For instance, I've spoken to the Nuclear Regulatory Commission in the United States, and I said, do you want me to show you how this is safer than what we have today? And by and large, much of the response has been, no, we want you to show how you adhere to each of these steps that we've laid out. And I said, well, these are fine steps if I was a pressurized light water reactor. But my machine doesn't even have some of the items in here that you're talking about, nor can it undergo the accidents that you're worried about. So these things are gone from the beginning. They're designed out from day one. And to have a regulatory approach that recognizes that and says, let's talk about objectives rather than exactly how to accomplish the objectives. Everyone wants safety. Nobody wants to have nuclear accidents or radioactive releases that harm the public, least of all nuclear engineers. That's why we're fascinated by a technology that could potentially eliminate the root causes of this taking place. And so I think that a regulatory reform which will be instigated at the political level will be the required step needed to free up capital markets.
Very much. Yes, that's another question. Go ahead.
Yes, my name is Kees de Lange. I'm a member of the Senate in the Netherlands, and in fact, I'm the only physicist in the entire Senate. And that's exactly where one of the problems lies. When I look around me every week, I notice the tremendous lack of knowledge about the physical sciences in general and about nuclear energy in particular. So it would help tremendously if only a few people in this audience would take the courage and get active in politics and change the tremendous lack of knowledge that I experience every week. Please, your comments.
My first comment.
Was that a question?
I do have a comment. My first comment is how fortunate the Dutch people are to have at least one senator who has a background in physics. In the United States of America, we don't have any. So, yes, it would be wonderful if more engineers, scientists, doctors, teachers pursued politics. It seems that lawyers seem to be more attracted to that field of work. But,
unfortunately, yes.
Yeah.
Are the construction costs of a molten salt reactor significantly higher or lower, different, than a traditional light water reactor?
We anticipate the construction costs will be significantly lower because of the operation at low pressures, as was mentioned earlier, and the reduced safety infrastructure needed because of you've eliminated essentially so many of the accident scenarios. But furthermore, let me expand that answer a little bit. If you look at the steel, concrete, all the materials that even go in today's light water reactors, and then you look at the final cost, the materials only account for a few % of the final cost. And then you add fabrication and transportation, all these things. I have a friend who's a professor at UC Berkeley, and he's added this all up, and he said, I can only account for about 25% of the cost of the light water reactor. Where's the other 75% of the cost? We both looked at each other and said, the regulation. So if you've got a machine, even today's machines, that really are probably 4 times more expensive than they should be, there really needs to be a question answered. Are we as societies, as free societies, deploying our capital, not just capital from banks and so forth, but our capital as people, our capital as time and resources, properly, and is nuclear regulation proceeding intelligently? I will leave that as an open question to people far more qualified than I to answer.
Can you give an estimate of the electricity price?
A great deal of the price of the electricity will depend on the ability of the reactor to produce co-products, because each of those co-products will be able to reduce the burden of the reactor. For instance, with today's reactors, it's difficult to desalinate water. If you desalinate water, you take away from the electricity production of the reactor. In these reactors, because they're high temperature, there's a potential there to desalinate water. And so that may be a very large co-product that could reduce the burden of price on the consumer. I think if we were looking at it strictly from an electricity production basis, it should be comparable, if not less, than today's light water reactors. That probably will not happen in the very first one, just as it did not happen in the first light water reactor, but will happen as we have developed a number of them and begun to build that design basis for it. But I really do think that there are going to be many co-products that are going to be able to reduce the cost of the electricity from the reactor.
Okay, I wish you all the success you need with FLIPE, and thank you very much for being here.
Thank you very much.
From President.